Okay, today we're going to talk about water and solutions and acid-base reactions as well, because most of those do occur in water solutions. But first of all, core concept about all of this is that water and the solutions of water have unique properties, and very thankful for that. We are water-based creatures. The properties of water is, first of all, it's a major constituent of all living things. It's almost a universal solvent. There are acids are water-based solutions, and they will chew up almost anything. Solid phase is less dense than liquid. That's a key factor right there. Ice floats. Without that property right there, we would have a very, very different environment. Water is a very high heat, high specific heat. In other words, it retains heat quite well and leads to climate stabilization. If you have a river or something flowing near your orchard or something, for example, it helps keep the temperature more moderate when you have the type of swings that we have here in the Ozarks during the spring. Also, there's the latent heat of vaporization. This is very important for us as well, because this allows our sweating to through evaporative cooling to cool our bodies down. And all of these result because of the water's chemical structure. As we saw in the lab last week, water has a bent configuration with the oxygen atom here, the two non-bonding pairs, and the hydrogen atoms off of here. And these non-bonding electron pairs also lead to bonding, not chemical bonding, but a different something called hydrogen bonding between the various molecules. And it's this hydrogen bonding that gives water all of its unique properties. Okay, so this is not a formal bond. There's an attraction there. It is nowhere near as strong as these bonds that connect an individual hydrogen here to the oxygen molecule, but it is strong enough that it gives water the unique properties. For example, it's responsible for why ice floats. Normally, as you decrease temperature, something becomes more dense, and that follows for water as well, up to a point, until you get to about 4 degrees centigrade. Once you get to 4 degrees centigrade, all of a sudden, because of those hydrogen bonds, it starts to decrease in density. This decrease in density is why ice, which is formed at 0 degrees centigrade, floats over the other water at these other temperatures. Also, water is important for the dissolving process. Components of a solution of solvent is the one in a larger amount. Solute is the component that's dissolved. Key definitions right there. Okay, solvent, a large amount; solute, the little bit amount. Now, when you add water to these different ones, solids, liquids, gases can all be dissolved in water. And you can see you have individual water molecules surrounding this ion, and you've got individual water molecules surrounding this ion. And this is how they actually exist in solution. You don't have one just stark charge somewhere in there, but as that salt crystal is dissolving, it's dissolving because these are coming in and separating them away from these other ones here. And there's actually heat evolved during this. That's called the heat of dissolution. There are limits on solubility. Certain things will dissolve. Also, some things don't dissolve that well. Polar substances, for example, only will dissolve in polar substances. Nonpolar substances will not dissolve in polar substances. That's the difference between oil and water, right? Oil does not dissolve in water. You can shake it up and you can get little tiny particles there, but they will eventually separate back out. So there are limits on solubility in terms of what the particular material is that you're trying to put into the water. But you can have miscible fluids. They mix in any proportion without separating. An example of that would be ethanol and water. They mix in all proportions. Gases and small intermolecular forces, they also mix completely, right? But as I mentioned, for some of these polar and nonpolar combinations, you then form immiscible, or things that do not mix. Okay, the idea of like dissolving like, this is just more information about that. Now, we can overcome that. That's the reason why we use soap when we wash dishes and our clothes and all of that, because soap provides both a polar and a nonpolar environment, right? So you have a ionic side of the soap, and this will help dissolve which is soluble in water, and then you have these that are soluble in oil. And so the oily dirt can then be taken up into the water by this portion of the soap dissolving that grease or whatever it was on your cloth. So the other key concept here is concentration. Concentration is the relative amount of solute in solvent. So it's kind of relative. For concentrated, means you have a large amount of solute. For dilute, there's a small amount of solute. But what we do is we measure concentration in terms of something called molarity. It's the weight by volume, okay? So you can have the concentration ratios of parts per million, parts per billion, volume, weight, all these different ones. So what we were talking about is the mass dissolved in 1,000 grams of solution. Okay, well, it just so happens that water has 1 gram per milliliter, right? So 1,000 grams of that would essentially be 1 liter of solution. And that's the way in which we usually are talking about all of the solutions that we are talking about. We're not talking about just percent weight or but it is a way of looking at it in terms of percent volume. And that is molarity. Moles are the solute in 1 liter of solution. So the moles of solute divided by the liters of solution gives you the molarity. And that's a key parameter for all of the different work that we're going to be doing in the rest of this chapter. Okay? Molarity is the moles of solute, what's dissolved in the solvent, the liters of solution here. Okay? So, some ionic compounds do not dissolve in water. They're called insoluble compounds. They do somewhat dissociate into ions when placed in water, but compounds that do dissolve by dissociating are called soluble. Okay? So in reality, even insoluble compounds dissolve to some small extent. They are sparingly soluble. An equilibrium exists between the precipitate and its ions. So if you've got an equation here where now instead of a chemical reaction, you're talking about a solid dissociating into its respective ions. So here you've got a solid in solution there, and AQ means that it is in water, right? And so this is a silver ion and a chloride ion that have been dissolved from this silver chloride. And here this K is much, much less than 1. K is called the equilibrium constant. It represents the concentration of the products divided by the concentration of the reactants, each raised to the power given by the coefficients in a balanced chemical equation. So each of these has a 1 in front of them, right? So you don't have to worry about any powers in this one. We'll talk about that later on in other equations. But the equilibrium constant represents the concentration of products divided by the concentration of reactants. These are the products. This is the reactant. When you have a solid, it's assumed that it has a concentration of 1. Okay? So you're not going to have to divide. So this right here, the equilibrium constant, is just going to be involving these two terms right here. For example, KSP, equilibrium solubility product, is called the solubility product constant. At equilibrium, the solution is saturated with dissolved ions. So this solid has as many of these ions present as possible. And different physical chemists over the years have measured these ones. And usually what they're doing is they're measuring at 25 degrees centigrade. Okay, 25 degrees centigrade. But you have to remember, the equations that we're going to be using are going to be used in degrees Kelvin. So 25 degrees centigrade is 298 degrees Kelvin. Okay, so just keep that in mind for when the temperature actually enters into the equation. So, like all equilibrium constants, KSP is a fixed value at a given temperature. This value at this temperature. The product of the two ion concentrations must have a value regardless of the direction in which equilibrium is approached. Note that any concentration of a solid is 1, as I mentioned earlier. So here you have the graph of different ones as a function of temperature. Here is 25 degrees right here, okay? So you can see that sodium nitrate has a solubility of this many grams, over 90 grams per 100 grams of water. Down here you have, this is sodium, this is where you would have the potassium nitrate right here. You'd have potassium chloride here, and you'd have sodium chloride here. Sodium chloride is fairly constant in terms of how it dissolves there. Okay, that's how much you're going to get over a very wide temperature range. So the concentration of a saturated solution that's how many grams will be dissolved in that material. It depends upon the temperature, as you can see here, and gases decrease with temperature. Okay, these normally are increasing with temperature, right, to a certain extent, but gases will decrease with temperature and will increase with pressure. That's a special relationship for gases as opposed to ionic materials. So in that prior slide, the solubility curve for sodium nitrate, potassium nitrate, potassium chloride, sodium chloride describe the amount of solute required to reach the saturation equilibrium at a particular temperature. And that graph shows the temperature in degrees Celsius on the x-axis and solubility in grams per solute per 100 grams of water on the y-axis. Okay. Now, that equation, though, that we talked about for predicting that solubility product coefficient, here is your general equation. This solid going to these two ions. Initially, all you've got is a solid. That would be a 1 right here, right? But you have 0 of these. Over time, you get an increase of each one of these. For every one of these that you get, you're going to get one of these as well, aren't you? And at equilibrium, this probably should have been a different letter. This is where it will be, right? So this is during the change, it's going to keep changing like that. And this is where it ends up at equilibrium. So in this equation, this times this would mean x here times x here. That's simply x squared. Okay? And this, by the way, is not 68. This is 63, right? It's 63. That's the slide made a mistake. I couldn't correct it. The square root of this right here is of 63 is no, I'm sorry. This is supposed to be 6.8 up here. This is the one that's wrong. It should be 6.8 up here. the square root of 68